Picking an overwrite address. Welcome back. In our previous lesson, we identified the exact offset at which EIP is overwritten in memory. That was a pivotal breakthrough. It confirmed that we not only crash the application, but also have the ability to control its flow of execution, the very essence of software exploitation. But now, we face the next critical question: where do we want the program to go? In this lesson, we'll answer that question by choosing a suitable jump ESP instruction to redirect execution into our shellcode. This is where exploitation shifts from passive observation to active redirection. We are no longer just crashing a program. We are taking control of what it does next. Let's begin. Why use jump ESP? In exploit development, our ultimate goal is to redirect execution flow to a memory location we control, typically the start of our shellcode. The problem is this: once we overwrite EIP, we can insert any 4-byte address we want. But how do we ensure that the instruction at that address actually transfers execution into our payload? The most elegant answer is to use the jump ESP instruction. Here's why. ESP points directly to the top of the stack. Our shellcode resides just after EIP in the overflow buffer, typically at ESP or close to it. So, if we find an instruction that executes jump ESP, we can insert the address of that instruction into EIP. When the application crashes and loads that address into EIP, it will execute jump ESP, landing directly into our shellcode. This is a clean, reliable way to bridge control from a hijacked instruction pointer to our malicious payload. However, finding a jump ESP instruction isn't just about picking a random address. There are strict criteria. We need to find this instruction in a loaded module that is not protected by ASLR, Address Space Layout Randomization. Why? Because if the module is randomized, the address of jump ESP will change on every execution, making our exploit unreliable. Fortunately, in our lab target, Windows XP running VLC 0.8.6d, most modules are loaded at fixed addresses. One particularly useful candidate is user32dll, a core Windows GUI library that is almost always loaded at a predictable base address in XP. Let's inspect it. Start VLC inside Immunity Debugger as we've done before. Press F9 to run the process and let it idle. At this point, we do not need to open the malicious subtitle file. Instead, we will explore the memory space of the process. From the Immunity menu, click View, Executable Modules. Window will appear listing all the loaded DLLs and binaries. Locate user32dll in the list. Note the base address, size, and confirm that ASLR and safe SEH are marked as false or disabled. This makes user32.dll an ideal candidate for exploitation. With user32.dll selected, right-click and choose Search. Then, Command. In the command search box, type jump ESP. Now that we've identified a valid jump ESP address, the next step is to incorporate it into our Python exploit, specifically at the exact offset we discovered during the EIP override phase. Begin by right-clicking the address in Immunity Debugger and selecting Copy. Then switch back to your Kali machine where the exploit script resides. I'll now append a comment next to the EIP placeholder to indicate the intended jump ESP address and its purpose. This will serve as a reference during testing, without altering the placeholder itself. Before inserting the address, recall an essential architectural detail. Intel x86 systems use little-endian byte order. This means that multi-byte values are stored with the least significant byte first. So, if our jump ESP address is hexadecimal 7E429353, we must represent it the reverse way in our payload as follows. x53, x93, x42, x7e. Update your Python script like this. Save the script and generate a new .ssa file. Now back to the Windows VM. I will first restart Immunity Debugger. Then, download the new file. Next, hit F9 to run VLC. Before proceeding, we need to place our breakpoint first. And finally, load the new SSA file. If everything is correct, the application will crash, but this time, EIP will be set to the jump ESP address, and execution will jump to the top of our shellcode space. To confirm this, in Immunity, press Shift F7 to step into the instruction at EIP. You should land on the top of the stack, where your C characters reside. This confirms that our jump has landed exactly where we want to place our shellcode. At this stage, we have full execution control. We've redirected the program flow. We know where our shellcode will land. And we've prepared the memory space for injection. This is a watershed moment. What began as a simple overflow has evolved into total control of a vulnerable process, all through carefully measured steps. In the next lesson, we'll explore how to clean this space, identify bad characters, and prepare a clean path for shellcode delivery. But before we go there, here are a few exercises to sharpen your edge. 1. Try searching for call ESP or push ESP/ret in other modules. How do they compare to jump ESP? 2. Explore different DLLs loaded by VLC and identify which ones are ASLR safe. 3. Try replacing the jump ESP address with an incorrect one. Observe how VLC crashes or misbehaves when execution flow is misaligned. These exercises are designed to sharpen your instincts and reinforce a practical understanding of exploit reliability and stability. The more you probe, the more control you gain.